Welcome to this presentation. I'm Dario Santonocito, a PhD student from the University of Messina. This work is entitled Evaluation of Fatigue Properties of 3D-printed Polyamide-12 by means of energy approach during tensile tests. This research activity is part of the collaboration between the University of Messina and the rapid prototyping company Skorpion Engineering. The aim of this work regards the investigation of the fatigue properties of 3D-printed Polyamide-12 adopting full-feed techniques, such as infrared thermography. The mechanical properties of the material were evaluated and the temperature trend of the specimen's surface was monitored during tensile tests. The fatigue properties are of fundamental importance for a proper design of mechanical component, but they are extremely time-consuming to be assessed. In this work, for the first time, the static thermographic method was applied to 3D-printed material in order to correlate the temperature trend to the fatigue properties of the material during tensile static tests, adopting a very limited number of specimens. Thermography has been used as an aid for assessing the fatigue properties of several kinds of materials. As observed by La Rosa and Risitano, if we cyclically test a material with a stress above its fatigue limit, the temperature evolution of the specimen monitored with an infrared camera is characterized by three different phases. An initial rapid increment in the first phase, then it reaches a stabilization temperature, and finally, in the third phase, a very high further temperature increment until failure. Generally, the higher the applied stress, the higher the stabilization temperature, but, on the other hand, the subtended area of the temperature number of cycle curve could be assumed constant and related to an energy parameter phi. If we report the stabilization temperature versus the applied stress, the fatigue limit of the material could be defined as the intersection with the stress axis. In addition, if we express in a stepped way the material and we evaluate the energy parameter at the different stabilization temperature, it is possible to obtain the number of cycles at which the material will be broke if cyclically tested with that stress, hence obtaining the S. The static thermographic method has been developed during the last 10 years. The first paper by Risitano and Risitano was presented in 2009. In 2013, Risitano and Risitano proposed the static thermographic method as a rapid procedure to derive the fatigue limit from a tensile test. During static tests of common engineering materials, the specimen's temperature is characterized by three phases. An initial approximately linear decrease due to the thermoelastic effect, following Lord Kelvin's law. Then, in the second phase, the temperature deviates from linearity until a minimum, and finally it experiences a very high further increment until failure. If it is possible to estimate the stress at which the temperature trend deviates from linearity, that stress could be related to a critical macrostress which is able to produce in the material irreversible macroplasticity. This critical stress is the same stress that, if cyclically applied to the material, will increase the microplastic area up to produce microcracks, hence fatigue failure. Static tensile tests were performed on specimens made of 3D-printed Polyamide-12 according to the geometry prescribed by the STM D638 standard, with a nominal cross-section of 13 per 7 mm. The specimens were realized with an HP Jet Fusion 3D printer along the XY plane, adopting the polymeric powder HP 3D High Reusability PA12. The printer adopts the multi-jet fusion printing system. It is a powder-based technology without the adoption of a laser source. The powder bed is preheated uniformly, and a first layer liquid fusion agent is deposited on the printing plane. Later, a second layer with detailing agent is deposited in the points where the material needs to be melted. A source of infrared energy, usually planar lamps, pass over the surface of the bed, allowing the powder fusion. The process continues layer by layer up to the completion of the component. The specimens were printed adopting the fast printing profile, which ensure a rapid printing process, but with lower mechanical properties compared to the mechanical profile. The static tests were performed with a servo-hydraulic load machine Ital Sigma 25 kN with a cross-head rate equal to 5 mm per minute at constant temperature and relative humidity. The tensile tests were carried out on 3 specimens, and an infrared camera FLIR A40 with a sample rate of 1 image per second was adopted to monitoring the specimen's surface temperature. Longitudinal displacements of the specimens were assessed by means of a digital image correlation system. The specimen surface were coated with an high emissivity black paint on one side, while with a speckle pattern on the other side. A series of fatigue tests at constant amplitude was performed on 7 specimens of the same geometry of the previous one, with a stress ratio of 0.1 and a test frequency of 3 Hz. In the plot are reported the engineering curves for the 3 tested specimens. The stress is evaluated as the ratio between the force and the nominal cross-section area of the specimen, while the strain as the ratio of the distance variation of 2 spots over the initial distance. The Young modulus has been evaluated as the linear regression of the stress versus strain between epsilon 1 and epsilon 2. This kind of material exhibits a linear elastic behavior followed by a smooth hardening until failure, and, in addition, it is not possible to assess a yielding stress. Considering the value of the mechanical properties for PA12 Type 1 specimens printed with fast profile along XY direction, as reported by the manufacturer datasheet, it is possible to note how they fall within the range of the average and 1 standard deviation for the 3 tests. The mechanical properties are also in agreement with other authors which investigated PA12 obtaining by laser sintering and multijet fusion system. During static tensile tests, the evolution of the specimen's surface temperature has been evaluated by means of an infrared camera. The applied stress is reported versus the specimen's surface temperature variation, estimated as the difference between the instantaneous temperature and the initial temperature of the surface recorded at time 0. The temperature data has been filtered with the Herrera-Laus filter, with a data span of 10% in order to reduce the outliers and highlight the thermoelastic trend. In the initial part of the temperature time curve, it is possible to clearly distinguish the linear trend of the temperature. Then it deviates from the linearity, reaching a plateau region. Suddenly, it experiences a rapid increment. It is possible to draw 2 linear regression lines, the former for the first linear phase, early stage of the temperature signal, delta T1 feed point series, and the latter for the second phase, last stage before the sudden increase in the temperature signal, delta T2 feed point series, not taking into account the temperature values near the slope change, experimental temperature series. Solving the system of equations, it is possible to determine the intersection point of the 2 straight lines. The corresponding value of the applied stress, sigma limit, could be related to the macroscopic stress that introduces the first plasticization phenomena in the material. For the free static tensile test, an average value of 29.4 minus plus 1.6 megapascal has been found for the limit stress. Useful information can be also retrieved observing the temperature trend. In particular, it is possible to define a yielding stress in correspondence of the temperature zero derivative flex region, in the transition point between phase 2 and phase 3. This stress can be thought as the macroscopic stress at which the majority of the material crystals are under plastic condition. A series of fatigue tests has been carried out with a constant stress amplitude equal to 28 and 30 megapascal. The test results are reported in a SN plot adopting a number of cycles for runout of 2 millions. In the same plot are reported the average value and the scatter band with one standard deviation for the limit stress assessed by static thermographic method. As is possible to note, both failure and runout tests fall within the scatter band, hence the stress value assessed by means of the static thermographic method could be related with the fatigue limit of the material. However, several traditional fatigue tests have to be carried out to obtain the complete SN curve and the fatigue limit of the material. After static and fatigue tests, the fracture surfaces have been evaluated through an optical microscope. As regards the static test, the fracture surface showed the classical aspect of a ductile failure with small plastic deformation. In all of the static fracture surfaces are clearly visible a series of defects due to the lack of powder melting. In particular, defect with a diameter of about 1 mm has been found surrounded by non-melted powder, where it is possible to distinguish the different layers. Fatigue fractures surface show a smoother profile typical of a brittle failure. The surface appears darker than the static case, and this could be addressed to the increase in specimen's temperature due to the fatigue test frequency. Defects due to the lack of powder melting with an average diameter of 0.3 mm have been found. Also in this case, the different layers of materials could be observed near the circular defect area, with an average length of the crack equals to 0.6 mm. From the analysis of the fracture surfaces, it is evident how the printing process affects the mechanical properties of the materials both under static and fatigue tests. In this work, the energetic release during tensile tests on 3D-printed Polyamide-12 specimens has been evaluated. The mechanical properties of the material have been assessed and compared to the authors and data sheet values showing good agreement. During the same tensile test, the infrared camera allowed the application of the static thermographic method, monitoring the specimen surface temperature. The average value of the limit stress has been evaluated as the stress level at which the temperature deviates from its linear trend, obtaining a value of 29.4 plus minus 1.6 megapascal. This value has been compared with traditional fatigue tests showing a relation with the fatigue limit of the material. Micrographic analysis of the fracture surfaces have been performed showing how the printing process severely affects the mechanical properties of the material under static and fatigue loading. The static thermographic method could be adopted in a rapid prototyping process as a fast test procedure able to predict the fatigue properties of the material from a conventional static test in a very short amount of time, 5 minutes per test, and with a limited number of specimens, even free specimens. Thank you for your kind attention.